Continuing on with the math instructions, multiply and divide. We're still working on the math instructions. We just completed add and subtract, and now we're doing multiply and divide. And of course, these four math operations or functions are the primary functions of mathematics: add, subtract, multiply, and divide. Keeping in mind that multiplication is multiple addition and division is multiple subtraction. However, that's irrelevant for using this in ladder logic. Probably the most important thing to keep in mind with the math instructions is that they execute every single scan that they receive a rung true in. Meaning, if the rung is true, and you can look on the screen here, I will turn off the enable. I'll toggle it off. Rung false out from this instruction, and so we have a rung false in. So neither one of these instructions will execute. Now with 500, you remember you could not put these two instructions in series because they were treated in 500 more like an electrical load. Well, we've moved way past that, and this is a much more efficient method of programming. So we're saying here that if this instruction is true, then multiply and divide. So it multiplies first and then divides. In the manual, we had some questions. Would either operation, multiply or divide, have any effect on the other? The answer is no, simply because if you look at the values, now in this case you created an array of integers called value, and this is elements 0, 1, 2, 3, 4, and 5. So nothing in this logic that gets executed has any effect on any other value in another operation. So if you look at the values in multiply, you have elements 0, 1, and 2, and then in divide you have 3, 4, and 5. Now if you were to use the same register, the same tag name, the same memory location twice in one of these instructions, then you could say that there was an interaction. But in this case, there is no interaction. Would it cause any alteration of the values of the destination memory locations if we reverse the order of these two operations? No, again for the same reason. We're using 6 unique memory locations for our math operations. There was another question: what is the result of 0 times 0? Well, 0 times 0 equals 0. And then 0 divided by 0. Now, I'm going to enable. You can see that one of these two operations, either the multiply or the divide, has caused an overflow in a minor fault. I'm using outputs here on your simulator to show that these bits are turned on. The reason you don't see them turned on is because they're cleared at the end of every scan. I'll show that in a minute. But I'm going to go aside from the manual here, and I'm going to split up these two operations into 2 separate rungs so we can determine which one is causing the actual overflow. So to do that, I'm going to copy and then paste. Now I have 2 identical rungs. I'll change this one to enable bit 1 so it's separate, and I will take and delete the multiply from this rung and the divide from this rung. Select them both. Well, I don't have to. I can just hit finalize all edits. Going back and forth between RS Logic's 500 and 5000, you can, it's not get confused, but you forget all of the latitude that you have in 5000 that you do not have in 500. So now this is still enabled, but you see we don't have the faults. So I will toggle that bit off, toggle this one on. Now you can see that it was dividing by 0, which is an illegal operation which causes the overflow. If you divide anything by 0, technically we might say that's infinity, and that's an overflow. Now we're dividing 0 by 0. You might say, well, 0 divided by 0 is not infinity. Nonetheless, dividing by 0 is an illegal operation. Now I'm going to put this back the way it was so we can continue. So I will double click on this rung and pull the divide back up to here. Delete this rung and finalize all edits. See, now we're back where we started. Toggle that bit and you see we have our overflow. So the overflow is on simply because we have a divisor, source B of 0. And I had you try to toggle these bits on and off from your keyboard to prove that they were actually being turned on every scan. I also had you temporarily move the overflow and fault rungs to the top program. In other words, move them up there or move this down here. Finalize all edits. Now, it may appear that these bits are no longer coming on, the overflow and the minor fault. Actually, they are. But because this clears every program scan, this operation right here sets these 2 bits, and then at the end of the scan, which is the next rung, the end statement, they're cleared, and when you come back to the top, because they're cleared, these are also off. So in other words, these are not set, so these 2 rungs are false. It turns these 2 bits off. You execute this rung, and it sets these 2 bits again, but then they're cleared. Now this is just a minor point, but I wanted to demonstrate that dividing by 0, source B just flat cannot be 0. That's really all there is at stake here. And if you do want to detect this kind of a situation, overflow or minor fault, you use these 2 bits, but you don't actually have to turn on outputs. You can use them elsewhere in your code. I'm going to put this back. Finalize all edits, and we're back. How does that compare to the previous order of logic? Well, the overflow and the minor fault reset at the end of the scan. Minor are true for 1 scan, set and cleared every 13 milliseconds, which means more than 5 times per thousandths of a second. So you could say 5,000 times per second that these are cleared. That's why you're not seeing them on. Do you think that the overflow error was eliminated by placing the status rungs above or at the highest point in the program? No, they were not. Change the value of 3 to 1, value 3 to 1 right here, so you can click, enter 1. What is the result of 1 divided by 0? Well, it shows 1 here, but you still have the overflow. So that value is not really legitimate. The fact that the overflow is on, this is where you would use this bit to declare that the result of this divide by 0 is not trustworthy. Change value 3 to 0 and value 4 to 1. So we'll make this 0 and this 1. Now you see the instant that our divisor is no longer 0, we lose the overflow and the fault. So what is the state of the minor fault bit? Off. Would you trust the destination value if the fault bit was set? No. We did our first logic, multiply divide, with double integers. We used 6 values or 6 registers, value 0 through 5 from an array of double integers called value. And we don't want to be prejudiced against floating point, so we did the same thing here with floating point. I had you add this logic, and you notice that we have a 1 in here for value 4, and that's why, even though this is enable, we are no longer setting a fault bit. So let's toggle this off and toggle this one on. And you see that our overflow and fault bit is back. What is the state of the minor fault flag? It's on. Why? A divisor of 0, whether dent or real, in other words, whether double integer or floating point, it's still illegal. Change the value of float 3 to 1 what is the result of 1 divided by 0? Well, it shows 1, but we know with the overflow and the minor fault, we can't trust that value. For further clarification of the minor status bit, open your controller properties and select the minor faults tab. You can see here that we have minor faults added and cleared at about the rate that I told you, about 5,000 a second. So you see it's accumulating up to a maximum value and then clearing that register. So if I click clear minors, it clears a bit. See, it comes right back because see, it still exists here. Now to prove this will disappear when I click here and toggle this off, so we'll have to go back to our properties. See, that has stopped accumulating and I can clear it and there's no minor faults. If I turn this back on, go back to controller properties, go to minor faults, now you see it's accumulating and clearing minor faults. This clearly illustrates what I told you, that they're being cleared every scan and then reset, because the firmware automatically clears them, but we're executing this rung of logic 5,000 times a second. So 5,000 times a second it sets the overflow and the fault, and 5,000 times a second it clears it. So the answer in your manual after step where we ask if the minor fault bit was still active, the answer was yes. As you glean the information under the minor faults tab, what do you see to support the above mention of a divisor of 0 being an illegal operation? Well, the fault is listed as instruction out of range. Now, if you've worked with enough automation hardware, HMIs, and controllers, if you try to enter a value that's not acceptable, it will tell you the value is out of range, but then it usually does tell you to enter a value between 0 and whatever. It gives you the legal range. We don't give you the legal range here, we just tell you it's out of range. Now I'm making a big deal out of this, so you don't ever do this. Try to divide by 0. How often was that minor fault occurring? I'm asking you these questions because they're in the manual. I already told you every single scan or 5,000 times per second, roughly 5,000. Now change float 4 to 1. So now we're going to be dividing 1 by 1, and as soon as let me leave that 0 and enable it again so you can see that it's faulted. Now I'm going to change it to 1. And you'll say as soon as that's accepted, it's no longer setting the overflow and the fault bit. Is the minor fault bit still active? No. Then I had you edit your logic as shown. We'll do that next. Okay, you can see that I've added the not equal float 4. That would be the divisor. Not equal to 0. I'm going to set this to 0. Because we know when it's set to 0, then the fault bits are on. So now we can see the fault bits there, and this is the rung that's actually being run. A rung being run. The R's in the green indicate that this logic is being executed, not this logic. When we finalize all the edits, then this rung will replace this rung. This new rung, or the edited rung, now controls the destiny, so to speak, of the overflow and the minor fault. Rung 0 up here is not being executed. Enable 0.0 is not true. It's off in memory, therefore this is false. But this is true, so it multiplies 0 times 0, which is 0. But F4, this value right here, for that reason this is false, not true. Now if I were to make this 1, then this is now being executed because float 4 is not equal to 0. If I make it 2, and of course 1 divided by 2, you already know what that answer is. You can see it's 0.5. If I go back to 0, notice that this rung is no longer being executed. Float 4 is 0. 1 divided by 0 is not 0.5. That right there indicates this instruction is not being executed. And the last thing that float 5, the fifth, or actually the sixth element of a 12 element array of real data types that we name float, the last thing that it heard was that it was to be set to 0.5 the last time this divide was executed. If I change this to 4, see, that's no longer equal to 0, so this instruction is true. True rung out, true rung in. 1 divided by 4 is 0.25, or 1/4. The answer to the question in the book, if your value for the divisor is 0, why is the minor fault bit, why is it not set? It's not set because the not equal instruction prevents a wrong true in to the divide instruction. The next thing I had you do was to change source A to 1 in both operations and change source B to -1 in both operations. Keep in mind that the not equal is not an operation, that's a qualifier. So the multiply is an operation and the divide is an operation. You see, in both cases you get a result that you would expect. 1 times -1 is -1. 1 divided by a -1 is -1. So this follows true arithmetical process that you would find on a calculator or any other device. So these instructions work exactly the way you would expect multiply and divide to behave. Then the manual had you change the -1 to 1 and the 1 to -1 in both of these operations, and you see the results are still the same. -1 divided by 1 is -1, and -1 times 1 is 1, -1. Now, some of you watching this may be far removed from your math classes. So next I had you change them both to -1. And of course you've already done this lab, so you know what the result was. I'm just curious if you knew what was going to happen before you made the change. If you divide a negative number by a negative number, you get a positive number because the division represents how many times you could subtract one value from the other. And in multiplication, -1 times -1 is 1. A minus number times a minus number is a positive number. And that's true no matter what the values are. If they're both negative, then the result is positive. Same thing with division. Then I had you put in values of 1000 and 13 for float 6 and float 7, and you got a result that you would have expected, right? 13 times 1000 is 13,000. Now on this next step, I had you add a division operation, and I didn't finalize the edit here because I wanted you to see it when I did it, just in case you missed it when you did it. But 1000 times 13 is 13,000. And then the next operation takes that value that's stored in the element of the float array, element 8, and divides it by 3. And you're going to see that the destination is now F float 8, which is the same as this register here. So 1000 times 13 is 13,000. So when I finalize this, what are you expecting to see for float 8? Are you expecting to see 13,000, or are you expecting to see 13,000 divided by 3? Now you're looking at this and you may say, well, this doesn't look right. This rung is true. 1000 times 13 is 13,000. But the value here is the result of 13,000 divided by 3. So as this rung is scanned, in other words, it scans rung 1, which is irrelevant here, Then it scans rung 2. It multiplies 1,000 times 13, puts 13,000 in there. You just saw it flick to 13,000. So it all depends on the update time of the video card in this monitor, whether you catch it in that, 1/5,000th of a second. Because remember, if the communication software happens to catch the value in float 8 in the controller at the right instant, it will display it as 13,000, even though microseconds later it's going to be 4,333.335. Now, if I swap these around, this wasn't part of the, oh yeah, I did. I swapped them around. So in the multiply operation, the float value is 13,000. Does that appear to be the correct result? Well, you could say no, or you could say yes, because sometimes you see 13,000, sometimes you don't. Now I had you swap these around. So I'll put that in the edit mode, drag this puppy over here. Now look. Maybe you'll occasionally see this display 4,333.3335, because there is an instant in time. Think about this. When this rung is being scanned, it's unconditionally true. And remember that these controllers only execute one instruction at a time. It's not executing both of these simultaneously. The value of 13,000 is fixed. If we divide it by 3, we get 4,333, whatever it was. Then we're multiplying 1,000 times 13, which has nothing to do with this operation. And it puts a result in here of 13,000. And so next time around, it's dividing 13,000 by 3, but we're not seeing 4,333 here because of the order that these are being executed in. And, oh, there it is, 4,333.335. So the communications interval, and remember that I'm doing Ethernet, which is 100 meg. Now, I wouldn't know how to break this down to show the non-synchronous relationship between the Ethernet transmission of packets of information and when this rung is being scanned, because remember, this rung right here is dividing 13,000 by 3. So this is 4,333, 5,000 times a second. But you're never really seeing it there unless everything is caught just right. Now, the only reason I'm making a big deal out of this is because remember that if you're doing maintenance, if you're even if you're a programmer and you wrote the program and you wrote it like this, you may not notice this and you may think that it's false, or you'll use these numbers in the wrong way. So you need to understand that when you use the same tag name or register or memory location in two different math operations, that there may be some interaction. Now, in this case, if you were to use float 8 for something else, you're probably going to get 13,000. You'll never see this. You'll never see 4,333 in your calculations. Anyway, enough said. In the divide operation, destination float 8 is 13,000. Does that appear to be the correct result for 13,000 divided by 3? No. However, we did see that 4,333.335 pop up at least once. You are at a point in the learning process that you should be able to explain what appears to be an anomaly. Please explain the apparent discrepancy in the results and the destination register in both cases. I already covered that. It depends which one you scan first, and the fact that the last one here is always going to be displayed the most often on the display. Now, if I add another rung, this wasn't in the manual, I'm just playing here. So I'm going to add another rung underneath of this one, and I'm going to multiply float 8 by 2. And I'll put it in float 9 since we're not using that. Look at that. 26,000. Okay? And that's what you would expect. I mean, right here it's 13,000. Right now, let's swap these back around. Now look what you got. See? So this is just something to be strongly aware of when you're working with math operations. And keep in mind, if somebody was making changes to someone else's program and didn't understand the relationship between the order that this is scanned and processed in and what you're looking at here, because float 8 is 13,000 for an instant, then an instant later is 4,333.3335. So you can see that the results are not the same over here based on which order these are scanned in. I think we've spanked that enough. That's it for multiply and divide.